Hey everyone, thanks for joining me. I'm Carl Lerche. I'm the lead of the Tokyo project. Tokyo is an asynchronous runtime for the Rust programming language, and I'm doing that work on Tokyo at AWS on the languages and runtimes team. And today I'm going to be talking about Rust, where it is used today, and also where I think it could be used in the future. So I'm going to be assuming you have some familiarity with Rust as a language. You don't need to even have written any, but at least have heard about it, know a little bit about the value proposition, some of the basic features, etc. I think this assumption will hold unless you've been living under a rock the past few years, as Rust has tended to, been a hot topic with tech news. Anyway, in case you haven't heard about it, Rust is a programming language that provides the same performance as C or C++, and it does this while maintaining memory safety, so your program will not segfault. What's novel about Rust is that it does this enforcement of memory safety at compile time instead of using a garbage collector like Java or Go do. So while Rust is still relatively new when it comes to programming languages, at this point, I would also say that it has grown past being a niche language to becoming fairly established. So the rate of growth over the past few years has been quite stunning, and it's gained adoption at quite a number of companies, both smaller startups and larger companies like Google, Dropbox, Microsoft. They've all spoken about using Rust. And of course, AWS, where I am, where nowadays we're using Rust to deliver services, including S3, EC2, CloudFront, Route 53, and some others. So Rust has really become, established. That said, I think the vast majority of this growth has been at the infrastructure level. So for networking type things, I'm talking about databases, proxies, routers, those kinds of things. What I don't see very often is Rust being used to implement higher level applications like API backends or web, mobile apps, that kind of stuff. Now, I'm not saying that nobody is doing that. I do know that some are. However, the majority of use cases today are at that infrastructure level. So I've been using Rust for about 10 years now, and for the first 8 of those years, I'd say that I believe personally that Rust was a systems level language that I probably would not consider it for web apps. And part of that is because Rust has pitched itself as a systems level language, but also that was kind of my early experience. That said, over the past couple years, I've started really asking myself, is this an inherent truth? Is this really something fundamental about Rust, or is there maybe some opportunity for it? Now, I'm not a Rust maximalist. I do believe there are, and there always will be, use cases that aren't well suited for Rust, and we should all be picking, the best tool for the job. That said, it isn't always black and white. You want a language that will enable you to be as productive as possible, but productivity has many dimensions. Like how quickly can devs implement features? How well can devs work together on the same code base? How quickly can new devs ramp up? What languages do they already know? Are they jumping between teams? Are there, what other languages are being used elsewhere in the org? Then there's quality. How easy is it to reach the necessary quality, both in terms of performance and defects? Now, realistically, different software projects are going to have different risk tolerances for accidentally shipping bugs. Also, how hard is it to maintain the software over its lifetime? So software tends to stick around a lot longer than we anticipate, and it takes time to, and effort to keep it running. So there are many things to consider when picking a language. We have to look at all these factors and do a cost analysis to determine the best tool for the job. So first, let's talk about quality, since I think that is really where Rust comes in the strongest, as it's kind of its entire value prop. Rust is a really good language for writing high-quality code, both from a performance point of view and from the point of view of minimizing defects. So on the performance side, being compiled and not having a runtime or garbage collector makes Rust code really fast. But speed's only part of it, because C and C++ have been around for much longer than Rust and are at equal performance levels. The novel part of Rust being its ownership-based type system that can prevent memory safety issues at compile time. And that's super important from a quality point of view, because with software written with C++, about 70% of high severity security issues are related to memory safety. But maybe a bit less obvious is that ownership-based type system goes beyond just memory safety. So developers are able to use that type system to design misuse-resistant APIs that can prevent a number of other bug categories. For example, with concurrency, the type system eliminates data races. So even simpler stuff like Rust's result type can help catch unhandled runtime exceptions at compile time. And I think result is one of the top things I hear when I ask devs what their favorite Rust feature is. And usually it comes with some story about how they caught a bug at compile time that would have just otherwise gotten them paged after the code was shipped. So the characteristics that make Rust good for high quality code also apply on the time dimension. It can be easier to refactor Rust code because the type system prevents errors that can accidentally introduce, often subtle accidentally introduce bugs, often subtle errors like accidentally introducing a mutation or holding a ref to the wrong object. Those get caught by the compiler. I do know that there are refactoring tools out there. It's not new. Java has some really good ones. I've used them. But developers that have worked on aging Rust code bases, and there are some now, do express that they can get through refactors quicker because the compiler handles more for them. So it eases the cognitive load of the refactor. You have to hold less in your head, and you tend to move quicker through the refactor, trusting the compiler. And this is especially true as the team starts to learn how to leverage the Rust type system to design their own application-specific misuse-resistant APIs. And if you have fewer bugs in your code base, it means you're spending less time debugging, issue reports, and more time building new features. And that's something I hear a lot from teams who maintain code in multiple languages. They find they're spending less time on the maintenance aspect with Rust. And that's a benefit that can apply to all levels of the stack, infrastructure or higher level apps. So now let's talk a bit about where Rust might not shine. So up until now, I think if all things were equal, Rust would be a pretty slam dunk sell, no matter the use case, infrastructure or higher level, but all things are not equal. So most of the complaints I hear can be summarized as Rust is not as productive, that it takes longer to build software with Rust than it does with other languages. I don't think this is controversial. You probably heard this as well. It comes up as stuff like fighting the borrow checker, or maybe you heard someone talking about Rust say, when it compiles it works, but it's really hard to get it compiled. And I think this impression is a fairly common point of view. So the trade-off devs are making right now is to trade higher quality code for longer dev time, but less development time than it would take you to reach the same level of quality in a language that isn't Rust. And that's kind of key right now. If you're building a database, for example, you want it to be fast and correct no matter the language you use. So in that case, it makes sense to use Rust because you will be able to meet the bar in less time. If you're willing to, prioritize less development time over quality, then it can make sense to pick another language. But is that actually true? That's kind of what I think a general consensus is right now, but I don't know if Rust is inherently less productive than other languages. So the first thing that started changing my mind about this, I was not hearing lack of productivity from teams that have successfully adopted Rust. In fact, more often than not, they expressed that their productivity did not drop measurably. The successful adoption stories I hear usually go something like, first, a team that has never used Rust is facing a unique performance requirement. So they decide that Rust is the best tool to solve that problem. They learn Rust, ship their software, meet their performance requirements, oftentimes with minimal tuning effort. And then they start to notice their software is running more reliably. They get paged less. And as they gain experience with Rust, they also notice that they're, as a team, roughly as productive as they were before. So they tend to start using Rust more and more for other use cases, eventually using it in non-performance critical areas, because as a team, again, they find they're just about as productive and can ship faster, higher quality code. So, why not use it? And especially as time goes on, the organization tends to start developing libraries that they can share across more use cases. So I've heard this story over and over again, and I found I had to reevaluate my own kind of personal assumption that Rust is less productive. Now, you may have noticed on that last slide, I qualified things by once they have successfully adopted Rust. So what I think is true today is Rust is harder to learn than most other programming languages for a number of reasons. So while it's true that Rust as a language isn't trivial, I think a bigger reason why Rust is harder to learn is that it's a pretty different language than any of the other most common languages out there. So it for sure is not an object-oriented language, even if it might look like that if you squint a bit. And trying to carry over object-oriented patterns to Rust will not work very well. But different doesn't necessarily mean less productive. So I think a symptom of fighting the borrow checker is more an indication of not having fully learned Rust. So it isn't so much that Rust is lower productivity, but more that Rust is harder to learn. Of course, being hard to learn is a real factor when considering overall team productivity, especially when first adopting Rust, since no one will know it yet, and it's a real issue. Second, and this applies mostly to using Rust at the higher level, but the Rust ecosystem is not anywhere close to as developed as, JavaScript, for example, for building web apps. There are web frameworks in Rust, but they are, more minimal. There are ORMs and database libraries, but again, they're more kind of raw or minimal. And I don't know how much of the standard tooling that you would expect to use in a batteries included web framework really exists in Rust today, which is kind of ironic because a lot of the modern web tooling is being built in Rust now. It's just not being built to be used from Rust. It's being like SWC, for example, is for using from JavaScript, but it's built in Rust. And then there's another aspect with this that stems from Rust's history of being positioned as a systems programming language. So many Rust libraries today prioritize minimizing raw performance over ease of use. So some libraries can feel clunky to use, and if you dig into why, it might be to avoid a few allocations here or there, which if you're building a web app, probably won't even be measurable at the end software product. And honestly, I've been guilty of this as well, and it's kind of something I'm trying to reevaluate. But anyway, a lot of library designs trade off maximizing performance for a more hard-to-use API. So I think in aggregate today, for the higher level use case, Rust is probably lower productivity because A, it's harder to learn, and B, the higher level library ecosystem is still lacking. B is kind of a chicken and egg problem. To solve that, someone, or more realistically, a larger group of someones, is going to have to decide to bite the bullet and invest there. But when it comes to A, I think there might be a quicker way to kind of think about that hard to learn problem. So when I talk to devs who say that Rust is hard, usually it comes down to either traits or lifetimes. Both of these topics are non-trivial, and if you're new to Rust and you structure code wrong using either these two features, it's pretty easy to dig yourself into a hole that's hard to get back out of. And I think that is a big part of what contributes to the feeling that Rust is hard or not productive. So once you are more experienced with Rust, and that experience comes over a non-trivial amount of time today, you will know how to avoid these pitfalls. But that isn't really helpful to someone who's trying to build something for next month. So what do we do about it? Well, if traits and lifetimes are hard, maybe the answer is as simple as avoid using them. So I don't want to make anyone angry, especially if you are big fans of Rust and love these two features, but I do think that most devs today could become very productive with Rust while barely touching these two features, and that is okay. The problem is right now, Rust learning materials will cover traits and lifetimes early on, and mini libraries will, in order to maximize performance, like I mentioned earlier, will heavily leverage traits and lifetimes. So right now, if you are getting introduced to Rust, you tend to hit these topics pretty early and as a core part of that learning experience, which is going to make that learning process take longer. So what I hope to see going forward is maybe library authors can try to, make their libraries easier to use, but also we can start building some learning material that prioritizes getting devs quicker, faster. And so I've been thinking about this problem, and I started compiling, a set of tips and tricks for using Rust in a way that avoids traits and lifetimes. These aren't just for beginners too. I tend to write my Rust this way as well. I'm going to go through these pretty fast. I'm not trying to teach you these tips and tricks, but more make you aware of them. You can always refer to this video back later or ping me for further discussion. So first tip, try to use enums when possible. So a trait in Rust is a way to define some generic code similar to interfaces in Java. And you need to use traits if you don't know all the possible types that you might be passing into a function. So like a library, you might want to write a generic function, and you definitely don't know all the possible types being passed in. However, in end products like services, databases, whatever, you do need to know all the types that are passed in. So you can use an enum that enumerates all those types instead of a trait. And that can greatly simplify the code. Of course, if you do that, it might add some verbosity, but there are crates out there that will use macros to handle that boilerplate for you, making it very streamlined. Incidentally, I actually do think macros are one of Rust's productivity superpowers, but that's a topic for another day. Tip number 2, similar to the first one, if lifetimes are hard, just try to avoid using them. So instead of returning references from functions, which requires lifetimes, return values, even if that means copying extra data. So you can measure later to find any bottlenecks from too much copying. Odds are it won't even matter. So start by just returning values. You can always pass in references as arguments to functions. Those don't need lifetimes. Again, I'm not saying never use lifetimes, but put it off as long as you can. Third tip, and that is to avoid accessors in favor of just making the struct fields public. And the reason for this is the borrow checker cannot see through method calls. So if you access data via an accessor instead of the struct field, you might run into cases where your code won't compile. Now, I know this one might feel bad, especially coming from an object-oriented language where using accessors is strongly recommended. However, Rust is not an object-oriented language, and accessors are one of those use cases where carrying over a pattern can get you into trouble. Again, there are definitely cases where you want accessors, just maybe start by defaulting to accessing fields. So speaking of Rust not being an object-oriented language, leads me to the next tip. Start by modeling data, not methods or objects. So don't get hung up on which struct a method is implemented on, because you may have to move it later to make the borrow checker happy. So one way to think about it is imagine that you only have free functions, you can't call methods on a struct, and you want to pass in as little data as possible to these functions. So doing that would require you to take a big struct with many fields and subdivide it into lots of smaller structs. So this process of subdividing structs is usually how you're going to solve most borrow checker problems, and eventually it'll become, intuitive. It's also why, if you look in Tokyo's internals, for example, you're going to see lots of structs named like shared, inner, synced, core, etc. It's because having many structs can end up being harder to name them, so I reuse the same names. But anyway, so if you're going to fight the borrow, if you're fighting the borrow checker, instead of reaching for like an RC or F cell, try splitting up your structs instead. On the previous slide, there was a link to an example to MiniRaft. I kind of set up that example as a bigger code example that shows how I would, subdivide structs, and something you can look at. So you may have also heard it said that you can't implement a doubly linked list with Rust as an example of borrow checker limitations. Well, that isn't true. You can implement a doubly linked list with Rust without using any unsafe code if you store nodes in a vec and use the indices to represent the links. In fact, this pattern can be highly useful and can be scaled up to complex data relations. I use this pattern often. The talk linked here in the slide covers this topic in depth. You should definitely watch it. Don't be fooled by the name. It applies to far more than just game development. Okay, so what is the point of all this? So I believe Rust could be an ideal general purpose language, including for higher level use cases. So fast, correct code is highly appealing. And if the ecosystem for those higher level use cases grows and matures to promote ease of use, then Rust could be very productive. And I also think that Rust is more different than you might expect after a first glance, and learning the language requires more than just learning syntax. It also requires learning new patterns. So to account for this, Rust really needs some learning materials that focuses on that, maybe prioritizes getting devs productive, skipping the advanced topics, putting them to later, because you don't really need them to be productive. We also really need a patterns book. So if anyone is motivated to write a book, please do. I'm not that person. So why am I even giving this talk? Well, given the audience, my guess is many of you are building infrastructure level stuff right now, and you've at least considered using Rust already, maybe already using it. And my guess is you will eventually be starting some new projects in the future that aren't as performance sensitive. So something where you might not immediately jump to Rust. What I do ask is, maybe consider Rust again, maybe help out build that missing ecosystem, because Rust is open source, the ecosystem is open source. And at the end of the day, someone or a larger group of someones are going to need to step up. And I think in the long term, it could pay off a lot, because it will end up making our software faster and more reliable. So with that, thank you very much. Oh, and I left my Discord, the Tokyo Discord, if you want to ping me. That's probably the easiest way.